All right, in this video I'm going to work on the problems from pages 340 to 342 using U substitution. Remember, U substitution is a strategy where we take a more complex problem and make a simpler problem in terms of U. Also, we want to remember that we're always looking for simple integration strategies wherever possible. We don't want to make the work harder, we want to make the work efficient. So in problem number 7, when I look at this problem, I see an inside quantity of 1 plus 2x, and I see an outside quantity of 4, and I think, would it be efficient for me to raise 1 plus 2x to the 4th power, and that would be a big no. So instead, this is going to be a perfect place to do U substitution. Now technically there's a 2 in parentheses, so you could say it's inside, but there's really no function operating on it other than the first power. So over here, I'm going to create my key to success. U is equal to the inside function 1 plus 2x. Remember, I take the derivative of both sides. So on the left side, the derivative of u is 1 du. And on the right side, I take the derivative in terms of x. The derivative of 1 is 0, and the derivative of 2x is 2 dx. All right, now at this point, now I got to go back and use my eyes to see if I can replace everything in the original problem. So I can replace a 1 plus 2x with a u, and I can replace a 2 dx with a du. See, it's right here. 2 dx is equal to du. So I'm going to write my new problem. This is just it's the same problem but simplified. In place of the quantity 1 plus 2x to the 4th power, I'm going to substitute u, and in place of the 2 dx, I'm going to substitute du. And you can see that that's a much simpler problem. When I find the antiderivative, I'm going to increase the power by 1 and divide by the new power. Plus c is not an absolute necessity in this step, because remember, that was just to get me a simple problem to get to my actual answer. So the last step is to replace the u back with its equivalent, which is 1 plus 2x. So this becomes 1 plus 2x to the 5th power over 5 plus c. Whoops, no antiderivative. Don't know why I wrote that. So that is my final answer. That is the antiderivative of the original function. Number 9. In number 9, I see a radical, and clearly 9 minus x squared is inside of that radical. I think it's probably beneficial and important for us to rewrite that for our math eyes as 9 minus x squared to the 1/2 power. And I have a negative 2x over here dx that I hope will appear. The inside function, 9 minus x squared, is being operated on by 1/2 power. So I'm going to let u equal to the inside function of 9 minus x squared. Take the derivative on the left in terms of u, and I get 1 du. Take the derivative on the right, and I get negative 2x dx. This is where I use my math eyes to go over and see, do I have a negative 2 dx? Yes, I do. That's a good thing. I'm going to write my new simplified integral. So on the inside, I'm going to substitute u in place of 9 minus x squared, and that'll be to the 1/2 power. In place of negative 2x dx, I'm going to substitute du. I'm going to increase the power by 1 and divide by the new power. Again, the plus c. It's probably a good idea to practice the plus c so that you don't forget it. And now I'm going to replace the 9 minus x squared in place of u. So my integration for number 9 is 2 times 9 minus x squared to the 3/2 power over 3 plus c. Don't forget the c. All right, let's go to number 11. In number 11, I see an inside function. X to the 4th plus 3 is being operated on by x squared. So now hopefully you're getting the hang of this. U is the inside function. Oh, by the way, you might decide that squaring this out and distributing the x cubed might be easier, and you could use the power rule. I'm not going to do that. I think it's probably about the same either way in terms of the amount of work you're going to end up doing. Derivative of u is du. The derivative of x to the 4th is 4x cubed, and the derivative of 3 is 0. And there's my dx. Okay, so this is my first time where I'm looking back over at my problem, and I see an x plus 4 or plus 3, so that's a good thing, but my du is equal to 4x cubed dx. Now I have an x cubed and I have a dx, so that's good. However, I don't have a 4. Well, that's easy mathematically. I'm going to divide both sides by 4, and that's going to become 1/4 du equal to x cubed dx. Now I have the x cubed dx that I'm looking for. The 1/4 will go out front as a coefficient, because when we replace the x cubed times dx, we're going to replace it with a 1/4 du. Now when I write my simplified problem, the 1/4, I can keep the 1/4 with du, but that would look weird. So I'm going to bring the 1/4 as a coefficient in front of the integral. That's an integral property that allows me to do that. I'm going to replace x to the 4th plus 3 with u, and that's to the 2nd power. I'm going to replace the x cubed times dx with, I've already got the 1/4, and then I'm going to put the du. I'm going to do the simple integration, which becomes u cubed over 3 plus c, which is, of course, u cubed over 12 plus c. I'm going to go back and replace x to the 4th plus 3 in place of u. So I get x to the 4th, yes, that's what I meant, plus 3 to the 3rd power over 12 plus c. That's my final answer for number 11. Moving on to number 13, let me slide this down just a little bit. My inside function, I'm going to start picking up the pace a little bit now because I think hopefully you've gotten the strategy. U is equal to x cubed minus 1. Du is equal to 3x squared dx. I have an x squared and I have a dx. Yay, but I don't need that 3, so I'm going to divide it to the other side. And now I have the x squared dx. The 1/3 is going to come in front as a coefficient. U goes on the inside to the 4th power, and x squared dx gets replaced with 1/3 du. Simple integration, u to the 4th over, u to the 5th over 5, plus c, which is the same thing as u to the 5th over 15 plus c. I'm going to replace u with x cubed plus 1, so I get x cubed plus 1 to the 5th power over 15 plus c. And that was number 13. Number 15. In number 15, I have an inside function of t squared plus 2. So I'm going to let u equal to t squared plus 2. Take the derivative du, 2t dt, use math eyes. I don't see a 2 over here, but I do see a t, so I'm going to divide the 2 to the other side. All right, I come back over here, I see a t times dt, so I'm good to go. My new integral becomes 1/2 integration of u to the 1/2 power du. So that's u to the 3/2 power divided by 3/2 power, which is times 2/3. The 2's will divide out, and that leaves me with u to the 3/2 power over 3 plus c. Resubstitute, and that gives me t squared plus 2 to the 3/2 power over 3 plus c. Number 15. Number 17. In number 17, I have an inside function of 1 minus x squared, so u is equal to 1 minus x squared. Du is negative 2x dx. Use my math eyes to come over here, and I see a 5. I see an x dx, so that's good because I have an x dx right here. So clearly I don't need that negative 2, so I'm going to divide it to the other side, just like I have before. And now I'm going to start replacing. So my new integral, my simplified integral, in place of the x dx, I'm going to substitute, I'm going to pull the negative 1/2 up front, but remember, there's already a 5 coefficient that I can also pull out front with that. So really that becomes 5, that was already in the problem, times negative 1/2, which is from my dividing the 2 on the other side. So that takes care of the x dx. And then in place of 1 minus x squared, I have u to the 1/3 power du. So that's going to become negative 5 over 2. Increase the power by 1 gives me u to the 4/3 divided by 4/3 plus c. When I simplify that, that's negative 15 u to the 4/3 power over 8 plus c. And then my final, when I re-substitute my 1 minus x squared, I get negative 15 times 1 minus x squared to the 4/3 power over 8 plus c. Number 17. Moving on to number 19. So I have an inside function of 1 minus x squared, and so I'm going to let u equal to 1 minus x squared derivative mathize. I see an x and I see a dx. That's a good thing because there's an x dx. I don't need the negative 2, so I'm going to divide it over to the other side. Now I'm happy. I'm going to replace, I don't think that's a negative in there, I can't really tell. So when I make my replacement, I'm going to have my negative 1/2 coefficient out front. I'm going to replace 1 minus x squared with u, so that'll be 1 over u to the 3rd power du. So that's my simplified version of the problem. Just so you know, ladies and gentlemen, if you're in my class, you can't integrate 1 over u cubed until you move that into the numerator. This is not an ln situation at all. So we're going to increase the power by 1, and that takes me to u to the negative 2. I'm going to divide by the new power of negative 2 and plus c it. I'm going to simplify that. That's going to give me positive u to the negative 2 over 4 plus c, which could be written as 1 over 4u squared plus c. Now, whether you leave the u to the negative 2 in the numerator or the denominator, if it's a show your work question, for me, it doesn't really matter. If it's a multiple choice question, then you might have to do some manipulation to match your answer to that answer. So I'm going to replace 1 minus x squared in place of u. So 1 minus x squared to the negative 2 power over 4 plus c. And you could write it again in either format. That's number 19. 21, very similar. On the inside, I have u equal to 1 plus x cubed. Du is equal to derivative 3x squared dx. Mathize, I come over here, I see an x squared, yay. I see a dx, yay. Over here I have an x squared dx, yay. I don't need the 3, so I'm going to divide it to the other side. In place of 21, in place of x squared dx, I will substitute my 1/3 in the front and my du in the back. So that's what's happening right there. I have a square power in the denominator. I'm going to go ahead and move it to the numerator and make that u to the negative 2 power. Reverse the power rule, and I get u to the negative 1 divided by negative 1 plus c. That becomes negative 1/3 u plus c. Make my replacement. Put 1 plus x cubed back in its oops, to the negative 1 power. I dropped that. So negative 1/3 and 1 plus x cubed to the negative 1 power, which of course could be taken to the denominator if that's how the answer was in the solutions manual or a multiple choice question. Just make sure you know that's just basic algebra. If you have a question on some of these little things, you can ask in class or in a help session. All right, that's 21. Let's go to 23. Problem number 23. So we're doing basically the same problem again. My inside function is that radical 1 minus x squared. Take the derivative of both sides. Du is equal to negative 2x dx. Mathize, I don't have a negative 2 over there, so I'm going to divide it on the other side. I do have an x and a dx, so we're good to go. So negative 1/2 out front. I'm going to bring that radical to the numerator, to the negative 1/2 power, and substitute my u. So I have u to the negative 1/2 power. Make sure I'm looking at the right problem. Yep. And then my du. Reverse the power rule, and that's going to take me u to increase the power by 1. So that's going to take me to the 1/2 power. Divided by 1/2 is times 2 plus c. The 2's divide out, and I have negative u to the 1/2 plus c. Replace back to the original, and I have the opposite of 1 minus x squared to the 1/2 power, and you could change that into a square root if you needed to, and the plus c is on the outside. All right, next is number 25. Okay, so number 25 got the fractions in it and maybe make people nervous, but no, I don't think so. So clearly the inside function is 1 plus 1 over t. So I'm going to let u equal to the inside function of 1 plus, when I rewrite this, I'm going to make 1 over t, t to the negative 1 power, because that makes a lot of sense since I'm taking the derivative. The derivative of du, u is du, derivative of 1 is 0, and the derivative of t to the negative 1 by the power rule is negative t. Decrease the power 1 by 1 to the negative 2 dt. That actually works out beautifully because that's the same thing as du equal to negative 1 over t squared dt. When I use my math eyes to come back over here, I see 1 over t squared dt, but I don't need the negative, so I'm going to divide the negative to the other side. And now I have exactly what I wanted, 1 over t squared dt. I'm going to write my new integral with my negative out front, and 1 plus 1 over t is replaced with u to the 3rd power. The 1 over t squared dt is replaced with the du and the negative. Increase the power by 1 and divide by the new power. Replace, so that becomes the opposite of 1 plus 1 over t. It doesn't matter how you write that. That's how it was written in the original, so that's how I decided to write it this time, and that's over 4. Number 25. 26. Don't use sub, ladies and gentlemen. Now we're getting to simple integration strategies. Total waste of time to use sub this thing. So the first thing I'm going to do in number 27 is I'm going to move the square root of 2x to the numerator and make that square root of 2x. Whoops, that's not what I'm going to do at all. Actually, not yet. I am going to move to the numerator, but before I do that, I want you to realize, and hopefully you know some things about radicals, this is the same thing as 1 over the square root of 2 times the square root of x. So the square root of 2x is the same thing as the square root of 2 times the square root of x. Why am I doing that? Because hopefully now you see that 1 over the square root of 2 is, by integral properties, a coefficient that can be moved into the front. So there I have the 1 over the square root of 2. I've gotten rid of that and I moved it out to the front. And so all I have left is 1 over the square root of x. So 1 over the square root of x is x to the negative 1/2 power. So hopefully you see I don't need any U substitution for that. I just have the variable x, which I do know how to anti-differentiate. No U substitution. I'm going to keep my coefficient of 1 over square root of 2. Increase the power by 1, so that goes to the 1/2. Divide by 1/2 is to multiply by 2, and there's my plus c. So in the numerator, I'm going to re-replace. I have a 2. I'm going to, oh, there's no substitution. Oh, what are you doing? Oh my gosh, children. I wish you were here to help me. Let's try that again. We're not doing U substitution. I got into a little habit there. So I'm going to keep my coefficient of 1 over square root of 2. The variable's plain x, so I'm going to increase the power by 1, so that goes to the 1/2. Divide by 1/2 is times 2, and then plus c. So I could write this as 2x to the 1/2 over square root of 2 plus c. No U substitution in 27. 29. I hope that you see Take Apart Miss Oliver Math. Take Apart Miss Oliver Math. It's a fraction, so I'm going to rewrite number 29 as x squared over x to the 1/2 power plus 3x over x to the 1/2 power. Take the fraction apart. Plus 7 over x to the 1/2 power dx. Now I'm going to do the algebra work, but the powers. That becomes x squared over x to the 1/2. That's 4 halves minus 1/2. That's x to the 3 halves. Plus 3. Subtract the powers gives me x to the 1/2. Plus 7, bring up the x to the 1/2 power and give it a negative 1/2 power. Now I'm going to do simple integration. Increase the power by 1, divide by the new power. Increase the power by 1 to the 3 halves, and so then I'm going to multiply by 2, so that's going to be 2/3 times 3. Increase the power by 1, so that's 7x to the 1/2 power. Divide by 1/2 is to times by 2. So simplified, that's 2x to the 5 halves over 5. The 3's here divide out, so plus 2x3 to the 3 halves. 2 times 7 is 14. X to the 1/2 power plus c. No U substitution. Use simple integration techniques where possible. Number 31. I don't even have a power other than 1 on the outside here, so I'm going to distribute. Use simple integration strategies where possible. T squared times t is t cubed. T squared times 2 over t is 2t dt. Simple integration strategy, increase the power by 1, t to the 4th plus 4 minus 2t squared over 2. Of course, the 2's divide out. T to the 4th over 4 minus t squared plus c. No U substitution. Simple strategies. Number 33. Oops, I didn't want to do that because that'll get rid of my highlighting. Number 33. I think it slid down as far as it'll go. Same thing. I don't have any power other than 1 on the quantity. This is y to the 1/2 power, so I'm going to distribute. So that becomes the integration of 9 y to the 1/2 power minus y to the 2 has 3 halves power dy. Increase the power by 1. That's y to the 3 halves times 2/3. Increase the power by 1. Y to the 5 halves divided by 5 halves is to multiply by 2/5 plus c. 3 divides into 9 3 times. That gives me 6y to the 3 halves power minus 2y to the 5 halves over 5 plus c. If I didn't make any errors. Could have You can let me know in class if there are errors. Hopefully I did not. All right, let's go on to the next set. So now we leave the algebraic expressions and now we get to the trig. So I'm going to go slow again in this section just to make sure that you hopefully get a good understanding of how the trig works. So I'm going to slide this over a little bit. All right. So let's begin with number 47. Now the inside functions are not necessarily always as clear with trigonometry. So some guidelines that I can give you is we're looking for an inside function. That's one thing that you want to pay attention to. Secondly, if you pick the wrong thing for u, it won't work. And that means pick again. You just didn't pick very well. So let's look at the first one. I have a coefficient of pi that I actually can get out of the way and put in front. I'm not too worried about that right now. The trig function of sine is operating on an angle, even though there are no parentheses there. There really always are parentheses after a trig function. They're just implied. So I'm taking the sine. I am operating on the inside function of pi x. Pi x is the angle that sine is operating on. So pi x is the inside function. So I'm going to follow my same U substitution strategy. I'm going to let u equal to the inside function of pi x. I'm going to take the derivative of both sides. I get du and the derivative of pi x. Remember, pi is the coefficient of x. It's like taking the derivative of 5x or 3x. So don't let the pi throw you. And the good news is I actually need that pi because I have a pi dx over here because this is when you use your math eyes. So the rewrite of that simply becomes sine of u du. Now, when you antidifferentiate trig, go really slow, tricky trig. The antiderivative of sine. So now you have to think, what function has a derivative of sine? Well, the derivative of cosine, think about it, is negative sine. So when I antidifferentiate positive sine, it takes me back to negative cosine of u plus c. So resubstitute, that becomes negative cosine of pi x plus c. All right, that's 47. Let's go on to 49. In number 49, same thing. Now, I may not work these all the way out because of time, but the inside function is 2x. The derivative of 2x is 2 dx. I don't have a 2 over here in my problem, so I'm going to divide that to the other side just like I did before, and that gives me dx. I'm going to make my replacements, so I have my 1/2 coefficient out front. In place of the 2x, that's where I'm substituting the u, and I'm replacing the dx with the 1/2 du. As we said in the last problem, the antiderivative of sine is negative cosine u, whoops, not du, eraser, there we go, plus c, and then I would replace the 2x in here, which I'm not going to show. Number 51. Don't be alarmed because you see fractions. I mean, I know we don't love them, but they're not bad. All right, so I'm looking for my inside function again. This is the same as the last problem. So parentheses around the cosines operating on my angle. So I'm going to let u equal to the angle, the inside function, and I'm going to rewrite that as theta to the negative 1 power. Theta is a variable. We treat it like we treat x. The derivative of u is du. The derivative of theta to the negative 1 is negative theta to the negative 2 d theta, not dx, but d theta. That's the same thing if we do a rewrite so that we can see what we need to see. Negative 1 over theta squared d theta. When I use my math eyes to look back over here at the original problem, there is no negative, so I'm going to divide it to the other side. So that's negative du is equal to 1 over theta squared d theta. I'm going to do my rewrite. The negative coefficient goes out front. There's the -1. In place of cosine, I'm going to substitute, or in place of 1 over theta, I'm going to substitute u, and there's the du. Now think carefully, tricky trig, go slow. What function has a derivative of cosine? The derivative of sine is cosine. So I get negative sine u plus c. Now the negative came from right here when we divided it to the other side, but when I take the antiderivative of cosine, I get sine. And then of course I'm going to replace my variable back in here to get my final answer. Mainly the purpose that, or what you need the video for, is actually identifying u and going through the process. Number 53, we have an E problem. An E problem. When you get to E, oftentimes these are hints. Often when you're working with E, you let u equal to the power of E. So when you have E problems, often, I didn't say always, I said often, these are strategies that you try. Let u equal to the power of E. So in this case, the power of E is 5x. So I'm going to let u equal to 5x. Du is equal to 5 dx. I don't have a 5 coefficient, there's your AP score, but I'm going to divide it to the other side, and I get dx. So when I do my rewrite, I get a 1/5 coefficient out front, e to the u, du. Oh, we love e because the antiderivative of e to the u is e to the u, and the derivative of e to the u is e to the, well, technically, yeah, du. So I get 1/5 e to the u plus c, and then my last step would be to re-substitute. Don't just leave it in terms of u. You won't get credit for that. I mean, partial credit maybe, but you won't get credit for leaving it in terms of u. I'm not rewriting in terms of x. You can do that. You can re-substitute. You've seen that enough in the other problems. So in other words, what I'm trying to say, just to be clear, is that the actual answer is 1/5 e to the 5x plus c. That should be your final answer. Even though I'm stopping, you have to continue on. Number 55 is another E problem. I'm trying to just drag this down a little bit. There we go. So in the next problem, my power is negative x to the third power. So I'm going to let u equal to the power of negative x cubed. Take the derivative of both sides, and I get negative 3x squared dx. I have an x squared, yay. I have a dx, yay, but I don't need the negative 3. Divide it to the other side, per usual, per normal. Do the substitution, the negative 1/3 coefficient out front. And then I'll have e to the u, which is ez. The antiderivative of e to the u is e to the u, and then I'll have my plus c. And then your last step is to substitute negative x cubed back in place of u as your final answer. Your answer has to be in terms of the variable it started with. 57. Ooh, 57 looks kind of interesting. Slide that down, 57. All right, so now I have two trig functions. I have sine operating on 2x, and I have cosine operating on 2x. All right, so I'm going to play the game and pretend I'm like, okay, I'm just going to let u equal to the angle measurement. By the way, this isn't going to work, so don't copy it. If you're please don't copy. I hope you're checking. 57. All right, so I'm just trying. I'm like, I think use the inside of 2x. So the derivative of u is du. The derivative of 2x is 2dx. I don't have a 2 coefficient, so I can divide it to the other side and get dx. And then when I replace, I get 1/2 antiderivative of sine u cosine u du. That really doesn't look much better, because I don't haven't memorized anything that has a derivative of sine, cosine. So whatever shall I do? Well, this is exactly what I was saying earlier if you've watched the whole video. If what you pick for u doesn't work, pick something else. So I did not pick correctly that allowed me to integrate. So I'm going to restart. And now I got to pick again. So I can either pick sine of 2x or I can pick cosine of 2x. I'm going to pick one of those two to be the inside function. Now when I pick, I want to think very smartly about my trigonometry. Which one of these functions is the derivative of the other? Okay, hear that again. Which one of these functions is the derivative of the other? Think. Well, the derivative of sine is cosine, and the derivative of cosine is negative sine. So I can pick either one of them, but if I pick cosine, I have to introduce a negative. So the smart pick is to pick sine. Either one of those actually will work. So if I let u equal to sine of 2x du, now here comes, be careful, you've got to do the chain rule. The derivative of cosine, the derivative of sine is cosine 2x, chain rule times the derivative of the angle. You can't forget the chain rule. All right, now when I look at that 2 coefficient, I don't have one on the other side, so I'm going to divide it over. And the only way we'll know if this works is if we can replace everything and actually do the integration. So I'm going to have my 1/2 coefficient out front. In place of sine 2x, I can replace a u. And in place of cosine 2x, I can replace with the 1/2 du. Oh, that's beautiful. So that's 1/2, increase the power by 1 and divide by the power. That gives me u squared over 4 plus c. And then I'm going to replace the original u to make that sine squared 2x over 4 plus c, or you can just keep it like it was written and do it like that. It means the same thing. But if it's multiple choice, you might find your answer the first way that I wrote that up. Number 59. All right, so I've got tangent to the 4th power and secant to the 2nd power. Now, I know that there is a trig function that has a derivative of secant x, tangent x, secant to the 1st power, tangent to the 1st power. I know that the derivative of secant is secant x, tangent x. But this is tangent to the 4th power, secant to the 2nd power, and the angle actually is just plain x. So it wouldn't make any sense to let u equal to x. We never let u just equal to plain x. That won't get us anywhere. It just changes the problem into a problem in terms of u. So we're kind of back in the situation that we were in number 57. Now, really what I want you to pull out of this is not the right answer. What I want you to pull out of this is how I'm thinking about it. So now I'm focusing on the 2 trig functions with not ignoring the powers. I'm thinking about tangent and I'm thinking about secant. Is one of these trig functions the derivative of the other? So just let's take tangent by itself because that's first. What's the derivative of tangent? Secant squared. Perfect. Perfect, perfect, perfect. So since the derivative of tangent is secant squared, I'm going to let u equal to tangent x. Now you may be wondering, is that an inside function? Well, remember tangent to the 4th is tangent x to the 4th. So it's clearly an inside function. The point is they're not always written with the parentheses to give us a clue. All right, let's take the derivative of both sides. The derivative of u is du. The derivative of tangent is secant squared x. Yay, that works out beautifully. Let me erase some of this stuff over here. So let's start replacing. So in place of tangent, I'm going to substitute the u. That's going to be to the 4th power. In place of secant squared x dx, in fact, I forgot my dx, I'm going to replace with the du. I'm going to increase the power by 1 and divide by the power, plus c. I'm going to substitute tangent x, so that gives me tangent x to the 5th power over 5 plus c. Okay, let's go on to number, where are we? That was 59. Going to 61. Ooh, another trig situation. Very similar if you think about it. 61 is similar. Come on, slide down, scrolly bar. You can do it. There we go. 61 is very similar to number 59. We know that cotangent and cosecant have a relationship, so the question that we're asking ourselves here is, which trig function is the derivative of the other? Hopefully, like the last problem, you know that the derivative of plane cotangent is cosecant squared. So I'm going to let u equal to cotangent to the 1st power. That's an inside function, because remember, that's the same thing as cotangent of x to the 3rd power. The derivative of u is du. The derivative of cotangent is negative cosecant squared x dx. My problem does not have a negative, so I'll divide it to the other side. And my rewrite, I'll have the negative coefficient in the front. I am substituting cotangent x with the u, so that's 1 over u. And I'm substituting cosecant squared x dx with the negative du. Now be careful here. The antiderivative of 1 over u is negative ln absolute value of u plus c, because the derivative of ln u is 1 over u, or u prime over u. I'm going to substitute the u, so I have negative ln absolute value of cotangent x plus c is my final answer. 62. Okay, they're trying to be sneaky here. The antiderivative of actually cotangent squared x. So for that one, now be careful. The derivative of cotangent is negative cosecant squared. So do we know a function that has a derivative of cotangent squared? We don't. Now, the variable is just plain x. So it really wouldn't do me any good to let u equal to cotangent of x, because then that's going to introduce a negative cosecant squared. So am I stuck? Is this something that we can't do? Well, no, there is something we can do, because from our prior experience and prior knowledge, we know that cotangent is the same thing as cosine squared x over sine squared x. That brings us into a new situation, because we do have a relationship between sine and cosine. All right, so let's think about this. This is the same thing as, well, it's the same thing as cosine of x over sine x squared. This is going to, even though all of this is true, it's not going to get me anywhere with U substitution. All right, so there is one more thing that I'm thinking about from my prior experience with trig, with cotangent squared. So bear with me. This is going to go back into the deep recesses of your mind. We had 3 Pythagorean identities last year in pre-calc. The basic one is sine squared x plus cosine squared x is equal to 1. That's a Pythagorean identity that you learned last year in trig. Now, we're looking for cotangent squared, so if I divide each term here by sine, because I want to get I want to get a cosine or cotangent, divide every term by sine on both sides, that will give me 1 plus cosine over sine is cotangent squared equal to 1 over sine is cosecant squared x. All right, here's the cotangent squared, so if I get that by itself, that's cotangent squared x equal to cosecant squared x minus 1. Okay, that's not a bad replacement. So I'm going to rewrite this problem as cosecant squared x minus 1 dx. And now I don't even need any U substitution because I do know a function that has a derivative of cosecant squared. The derivative of cotangent is negative cosecant squared. So the antiderivative here becomes negative cotangent x. And the derivative of 1 is x plus c. So that one was a little bit sneaky, and you had to pull on some deep resources and think about the Pythagorean identities to actually get that one to come out. Didn't turn out to be a U sub at all. It became prior knowledge problem. All right, let's go on to number 65. We're almost done with this set. In number 65, we're back to E. Now remember I said with E, you often let U equal to the power. Well, letting U equal to X is never going to do any good. Well, in this case, E to the X plus 1 is on the inside of a power of 2. So I'm going to let U equal to the inside function of E to the X plus 1. I'm going to take the derivative on both sides and get du equal to E to the X dx. I'm going to make the replacements, and let's see, I have everything that I need. I have an e to the x dx, and I have an inside function of e to the x plus 1. So that becomes the antiderivative of u squared du, which is u cubed over 3 plus c. Make the replacement, e to the x plus 1 to the third power over 3 plus c. Number 69, break apart, break apart, break apart is my first reaction. The only reason that I'm not moving forward with break apart is I have a 2 to the x, or a power of 2x and a power of x. So can I break it apart? Absolutely. It's a strategy. It's a math skill. It's legal. But is it going to necessarily make this problem better? I could do it either way. I really don't know how I want to do it. I think I'm going to keep it. I think I'm going to keep it this way and see what happens. And that's what this is all about, like making a decision and trying to just see what happens with it. So I'm going to let, since I have a 2x here power, I think I'm going to let u equal to e to the 2x and see what happens. Is that what I want to do? Let's see. The derivative of e to the, so if I let u equal to e to the 2x, I might go back and do a break apart. We'll see. If I let u equal e to the 2x, I get du is equal to e to the 2x, so e to the power times the derivative of the power. That's really not going anywhere. So I'm actually not going to do what I just did. And ladies and gentlemen, when you're doing these problems, this is what you have to do. You try something, back up, try something else. So let me look at it again. All right, let's go back and try break apart. If I break that problem apart, that would become the integral of 5e. Let me do the rewrite just so you can see that, because many of you are doing the break apart just fine. Some of you are struggling with break apart. So if I break that apart, that's 5 over e to the 2x power minus e to the x over e to the 2x. Simplified, that becomes 5e to the negative 2x minus, now when you have e to the power, you subtract the powers, so that would become e to the negative x. Now, if these had been e to the positive x, I'd be really, 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 really happy, but not. So I'm going to treat these two terms independently of each other. In other words, I'm going to do an antiderivative. I'm going to get 5 out of the way. I'm going to do an antiderivative for e to the negative 2x dx minus separate antiderivative e to the negative x dx. Integral properties allow me to take this thing apart. That's why you need to know your integral properties. So I'm going to do this just so you can follow me. I'm going to say integral number 1, and over here is integral number 2. So in integral number 1, I'm going to let u equal to the power of negative 2x dx. I'm going to take the derivative of both sides. du is equal to negative 2 dx. So I'm doing 2 separate u sub situations, and sometimes that happens. So I don't need the negative 2, so I'm going to divide that to the other side. I'm going to make my replacements, so that'll give me negative 5 halves integral e to the u du. That's really nice because that just becomes negative 5 halves e to the u for term number 1 when I go back to make my replacement. For term number 2, since this is not plain x, I'm going to let u equal to the power of negative x. du is negative dx. I don't need that negative, so I'm going to divide it to the other side. That becomes negative du is equal to dx. I'm going to rewrite the integral, negative coefficient in the front, and that becomes e to the u. That's nice. So that becomes the opposite of e to the u. And we will put our plus c on there. So when I rewrite my final answer and go slow and carefully here, I'm going to have from term 1, negative 5 halves e to this u, which is negative 2x. Now be careful, we had a negative here and a minus here, so that becomes plus e to this u, which is negative x plus c. So you might need to redo that one. You might need to watch and listen to that again and then go back and do it yourself to make sure you can do it. And then finally, number 71, let's clear the board here one last time. So let me use my math eyes. What do I see? Let me create a little more paper here. So I see e to a power and I see cosine. Both of these have an inside function. Cosine has pi x on the inside. E has sine pi x. So I could pick either one of those. Not both of them will work. But I'm thinking with my math eyes, the derivative of sine is cosine. So I think I want to pick u to be sine pi x. If it doesn't work, I'll pick again. The derivative of u is du. The derivative, watch out for the chain rule here, the derivative of sine is cosine of the angle times the derivative of pi x, which is pi. Make sure you hit the chain rule. I don't have a coefficient of pi in my problem, so I'm going to divide it to the other side. That leaves me with cosine pi x, which is really exactly what I want. So my replacement, I'll have a 1 over pi coefficient out front, e to the u, and I'm replacing cosine pi x dx with the 1 over pi du. Simple problem. The antiderivative of e to the u is e to the u. So I'm going to make my, well, no, I don't want to put equal, make my final replacement, and that's going to be 1, I'll put the pi in the denominator, that's going to be e to the sine pi x over pi plus c. So hopefully you were able to work through some of those. Hopefully this video has helped you.